curvature of a plane curve that has an equation y equals f of x. So for the special case of a plane curve with equation y equals f of x, we choose x as a parameter and write, writing this in our parametric equation or vector format but now it's in terms of x. So if we have r of vector function of x, and then just write this out in our standard basis vectors. I'm going to write x component, there's the xi vector plus, now I'll just put, for completeness, put the full thing y, this is going to be their j, but then y is a function of x, in other words, it equals f of x, so this equals to xi plus y is going to be, well, f of x, like that, j. Alright, so now the next setup is, well, we need to take the derivative, because again, we want to find the this setup here, the derivative right here, and then we'll take the cross product and so on, and then divided by the magnitude of the derivative, the first derivative cubed, and so on. So we need to take the magnitude of the cross product. So to get that, we need to get the derivatives. So this would be, or actually I'll write then, just because calculus book was writing then. So anyways, then we're going to get a r prime of x. This equals to, well, derivative of x is just 1, so that's going to be just I, plus, now derivative of this fx is just f prime of x, like that, j. Alright, so we have that, and so now the second derivative, that's again, calculus book just wrote and, so I'll just do that as well. So r double prime of x equals 2, and now the derivative of this one is constant, just becomes 0, so that just vanishes. So in other words, we're just left with this right here, so equals to f double prime of x. And this is going to be, j. Yeah, j standard basis vector, like that. All right, going further. So now since, because we're going to be taking the cross product, so since I cross with j, because these are perpendicular, this obtains the k. This is just the this is just the I, this is the x or the I. Yeah, and then this is going to be the y or the j, and then you get the cross product, it becomes all, these are all perpendicular. So you all get that, and this is going to be our z or k vector. Anyways, I'll recap on this in a bit, but I just wanted to illustrate that right now if you're confused. All right, so this is going to be k, and also note that if you have the cross product with itself, again, as I stated before, is 0. So j cross j is equal to 0. Equals to 0 vector. So since that, then I can just take the cross product, and then we can analyze that as we go. So we get r, the first derivative of r of x, r prime of x, cross with r double prime, vector function of x. This equals 2. All right, yeah, just fix that up, the bracket. This is going to equal 2. Well, let's plug these in. So the r prime is going to be that. So that's going to be I. So yeah, this is pretty interesting using these standard basis vector format like that. Plus, the vector f prime of x, j. And then cross with, well, this one here is just, the second derivative is just f double prime. So f double prime of x. And this is going to be, I'll try to make the x look different from the cross product. Like, I'll make it bigger. So just because we have an x already. I'll make it bigger like that. Okay, one more try. All right, perfect. All right, and then, this f double prime of x, and this is j. So again, it's a vector with no x component, or the x component 0. All right, so what we end up having is, well, we could just take these, multiply these inside using just basic vector function properties for cross product. This is going to equal to I cross with f double prime. Actually, and this is a function. This is just a scalar, so we can move that out of there actually. So this just becomes, I'll just take this out, put it in the front, f of x, f double prime of x, put it out like that, and then put another bracket. But we're gonna have I cross with j, like that, and that's the one that's equals to the k there. This equals to k vector. And now the next one's going to be, well, this is going to be multiplied or cross product inside, so just to FOIL this out. And this is f prime, and these are scalars, so we're going to get is a f, I'll put another bracket, just get these out of there. And this will be, let's put a, actually we don't need to put a bracket, put a bracket on the other one. So f prime of x multiplied by f double prime of x, and then times it by, and now we'll put the j cross j. So, and a cross product of a vector with itself is just 0 vector. Yeah, so this equals to 0 vector. All right, so in other words, this whole thing vanishes. So all we're left with is this, and this equals just the k there. So this equals to f double prime of x k, like that. Yeah, so that is so that is the cross product. It's fascinating stuff. Actually, but instead of circling this, that's not what we actually want. We want the length of it. So I'll write. I'm just gonna go. I'll say thus: the magnitude of r double prime. Yeah, I mean r prime of x cross product with the double prime of x r function like that. This equals to, well, this is just going to be square root of the term, all the components squared. So in other words, square root of f double prime of x, and then this is all going to be squared. But then we have a square root and squared, that just equals to f double prime of x. So that cancels out, and we're just left with itself. Like that, yeah. So that is the magnitude or the length of that cross product, and that's what we're going to use in our equation. And yeah, actually I just moved things around, but actually to be more accurate, because this is yeah, we're going to need the magnitude. This is squared, and then this whole thing square root, and the inside has to be positive. This is actually the absolute value of it, and this is not length because this is not a vector. So yeah, we also need to take the absolute value. So equals to this. Yeah, so that is that. Yeah, just make sure we have this, and I'll put a another box around. So it's absolute value because we only want the positive values of it, not the negative, because it could be negative and so on. So anyways, so that's what we have. And finally, we also have, so yeah, so we have this. Now the next component that we need for our equation, scroll back up for this. So we have the top. Now we just need the length of the this vector. Yeah, the first derivative vector function. So we just need that one. And so we also have, and we know this from earlier, from like way back in the beginning of the video. So we also have when we have just a y equals fx function, so we have this length right here of the first derivative. This equals to, yeah, we can go all the way back to the beginning of the video just to show you, or we can drive it ourselves. Anyways, I'm just going to scroll up. All right, yeah, so I'm back here. So yeah, again, remember the length, yeah, that's just going to be equals to that integral, but there's that inside term there. That was our r first derivative, r prime, yeah, of the vector function. Yeah, so that's going to be this 1 plus and then f prime of x squared. This is for if f, yeah, this is for the y equals fx curve there. And then, of course, I showed that, yeah, all these are just the same thing as writing the magnitude of the first derivative of that vector function. Yeah, so that's what we have here. So that's the length, this square root part. Yeah, so that's what we have, but yeah, anyways, I teleported back here. But we could also just take this again for completeness. Let's just derive it as well. So we have this right here, so the magnitude of this. Again, it's the same thing as I said way back in the earlier beginning of the video. This is going to be the magnitude of I. Yeah, this is just to be I plus f prime of x j. Again, the magnitude or the length, that just equals to now square root. And this is going to be this component squared. So 1 squared is 1 plus f1, f prime of x squared. Yeah, like that. That's it. Yeah, so we get that. I'll make this smaller. All right, yeah, so we have that. I'm going to box this because this is another part of our ingredients that we need. So that's why we put these together. So this is the top part, this is the bottom part. But then we need to cube it. Yeah, so again, scroll back up. And I keep scrolling because the terms are really big. Just wrap it around my head. Anyway, so we have this top part, we have the bottom part, and then cubed. All right, so thus, put it all together. Thus, we have the curvature. I'll put it a bit lower, so the curvature is equal to, and I'll put this k better. Curvature of x is equal to, again, I think it's put it for completeness. This is going to be Yeah, here, yeah, actually, I think I just wrote it in my notes. I'll write this is the original one we had. This is just for completeness. This is the unit tangent vector like that. Yeah, the derivative of the magnitude over this right here. Just write it in both terms. Then r prime magnitude of that. This equals 2, and then our second cross product format, just for completeness, x like that cross r double prime of x over r prime of x cubed. So this equals 2. So now our case, we're taking this part right here, and that's going to be this f, the magnitude or the absolute value of the f double prime of x. So absolute value of that, so we get the positive value divided by, and now this is going to be this is squared, square root, but then power cubed, that's going to be, this whole thing's going to be power of 3 over 2. So now we get 1 plus f prime of x squared, and then the whole thing is going to be, yeah, actually, calculus book, actually, instead of using the inside the square bracket, I'll use this as a just another bracket, and the big one we'll do squared over, yeah, that's power of 3 over 2. So there it is, that's our curvature. Yeah, so that is our curvature formula. I'll put this like this. This is curvature for the special case, the kappa, write this kappa better, like that. And this is a special case where we have a plane curve y equals fx. So epic stuff there. All right, and now we have that. And also now just a quick recap from my earlier video on standard basis vectors, just to illustrate again what they were, because we were using the fact that this I cross j, I cross product j equals to the k standard basis vector, and this one j cross j is equal to 0. So recall standard basis vectors, that's just along the x and y components. So we have the k is on the vertical one. This is the j. The j is on the y, and the x is on here. And these are again perpendicular. So if you cross this one with this, you're going to get this positive one actually. There, it's pretty fascinating, and you can do the cross product yourself, and you'll find that, and so on. And then so basically, when you have a vector from the origin, position vector up to this point, a1, a2, a3. Its components, you could write them in the x, y, z, the triangle bracket, or just put them in the standard basis format, indicating it's all vectors. So you're adding up all the vectors together. So it equals to a1i plus this. So it goes from the bottom, and then if you add 3 dimensions, you need another one, a3. So it goes all the way up. So you add them. So it's just vector addition. And yeah, so j I cross j is equal to k. And if you have any of these crossed by itself, parallel equals 0. Anyways, pretty epic stuff. All right, and now let's continue further and now look at example 5. So curvature of a parabola. So we're asked to find the curvature of the parabola y equals x squared. So again, this is y is just a function of x at the points 0, 0, 1, 1, and 2, 4. Well, again, we have our equation for curvature right here, which equals to the absolute value of the second derivative of f of x, f double prime of x like that, and then divided by this right here. So what I'll do is I'll just copy this just to make things easier. Whoops, I'll scroll back up here. I'll copy this and then I'll paste it there, so save some time. All right, copy and paste it right here. So this is our curvature, and now we just need the second derivative and so on. So yeah, so what we have is, let's just write this down. So we have y equals x squared, and again, this is just a function of x, like that. This is our f of x. Yeah, let's write that again. So f of x like that, and then the derivative we get, well, y prime is equal to, bring the 2 down to, and then subtract a power, so 2x, and again, this is equal to just f prime of x. Just for completeness, and then lastly, to take the second derivative, we get, well, 2. That's our f double prime of x. Again, same thing, just throw that in there, and then what we end up having is, put it like that, this is our kappa of x is equal to, well, 2 divided by, so the absolute value of f double prime of x is just 2. There, and then divided by 1 plus, and then f prime of x, that's this part right here, and then squared. So that's going to be like this. I'll put a 1 plus, or I'll put a regular like this. Actually, yeah, I'll just put it like this. Yeah, I'll just save time instead of, yeah, this is 2x, replace that over there. So plus 4x squared, 2 squared. Yeah, so yeah, 2x, 2 squared and x squared like that. And then all of that to the power of 3 over 2. So this is our answer. So that is the curvature of the parabola. Yeah, so y equals x squared. The curvature of it is just this. All right, yeah, so that's our curvature, and now the next setup is, well, we need to find the curvature at these points 0, 0, at the origin, at 1, 1, at 2, 4. So the curvature at 0, 0 is just at, at x equals to 0. Yeah, so we'll just put that in. That's going to equal to 2, and you can just see that right here. So we'll have kappa of 0 is equal to 2 over, well, 1 plus 0, and then power of 3 over 2. And then power of 3 over 2, 1, power of 3 over 2 is just 1, so it just equals to 2. So there it is. That's just like that. And now the next setup is, yeah, so the next setup is at 1, 1. So we're asked at 1, 1. The next one is 2, 4. So at 1, 1, the curvature is, you'll have kappa of 1 equals to 2 divided by 5, because if you put a 1 here, it'll just be a 1 and then be 1 plus 4. And then that'll just be 5. Yeah, so equals to 2 over 5 to the power of 3 over 2. And then again, for the calculator in my OneNote, you got to write it like this. And then you could just use the built-in calculator. And this equals to equals space. Yeah, so 0.1789 or approximately 0.18. And also, again, just to write this for completeness, if you write kappa of 1, this equals to 2 over 1 plus 4 times 1. So 4 times 1 is just 1. Yeah, so 4 times 1 is just 4, and then 3 over 2. So it equals to 2, 5, 3 over 2. So that's exactly this right here. All right, so that's what that is. I'll just box this in. And then the last one is at 2, 4. All right, so at 2, 4, well, x is 2, so then we'll just plug in, and this is a function of x, so we just plug in 2 in there. So k of 2 is equal to 2 to the power of 17. That's because 4 times x squared, so 2 squared is 4 times 4 is 16, and then plus that 17. So in other words, I'll just write this, and then we'll solve it, or calculate it. So this is going to be the kappa of 2. This equals to 2 over 1 plus, this is 4 times, well, x squared is 4. Yeah, so that's 16. 16, and then add them all up. This is 3, power of 3 over 2. This equals to 2, 17 to power of 3 over 2, like that. And then if you just write it like this, 2 divided by 17 to power of to power of 3 over 2, and just write it like this with the proper brackets, you can calculate it with the built-in OneNote calculator. For example, equals space, like that, and then this is 0.0285 or approximately 0.03. It's fascinating stuff. All right, going further. So observe from the expression for kappa of x, or the curvature as a function of x, or the graph of kappa in the figure below, and I'll draw that soon, that kappa of x approaches 0 as x approaches plus or minus infinity. You can also see this from here as well. As you go to plus or minus infinity, the bottom is going to be, well, 4 infinity squared, and then all to the power of 3 over 2. Yeah, this just gets infinitely large. So in other words, if you're dividing by infinity, 2 divided by infinity, you're going to approach 0. Doesn't matter plus or negative. So you're going to have it, so plus or minus. Yeah, so it's approaching 0 as x approaches plus or minus infinity. This corresponds to the fact that the parabola appears to become flatter as x approaches plus or minus infinity. In other words, it becomes straight and less, there's basically less curvature. And you can see this, I'll graph this all out right here. So let's see, and then I'll probably use the screenshot from Kako's book. All right, so let's say we have here, this is our x, and then this right here is our y. There's the origin, and then we have a parabola. Oops, we have a parabola like this, and then at the at y equals x squared, so at x equals 0, y is 0. It goes like this, but then becomes almost flat, almost straight, like that. And this is y equals x squared, like that. Yeah, so that's y equals x squared. And then now if we draw the other graph, I'll do this in red. So this one will do this in red. Yeah. This one is now, remember here it's at 0 at the origin, it's 2. So for the curvature, it's going to go at 2. It's going to be 1, 2. So this is at point 2, and then it goes as you go to infinity, it just smooths out. It goes like that. Whoops, I'll make it like this. It goes something like that, but it's actually a bit more smooth. I'll just draw it like this. All right, and then this one just goes like that. And this is our, this is at 2, and this is our kappa of x, like that. Yeah, also further, just to understand how the curve would look like, well, at 1, at x equals 1, we get this 0.18, so it actually goes much smaller. So this would be 1 roughly, actually, yeah. So if this is 1, so yeah, we'll just, yeah, if this from here to here, if it's 1, yeah, it should be somewhere around here. So this is 1, and then this would be about 0.18 over there. So again, it's not the x and y are not to scale, and yeah, this is going to be roughly here, negative 1 like that. So yeah, that's how it is. And yeah, I think I'll just use the, I'm going to erase this and just use a screenshot of the calculus book, because again, graphing manually is much harder than just using the actual graph like this. All right, so this is one from the calculus book. Again, yeah, it is much sharper up like that and goes down, goes back down like that. So fascinating stuff there. Yeah, so the parabola y equals x squared and its curvature function. So there it is, epic stuff. And again, note at 1 at x equals to 1 here. This is if you draw a cube from this one here. Yeah, so this is about 0.18. Yeah, so that's yeah, 0.18 right there. Epic stuff there. All right, furthermore, I've graphed this in Desmos 2D graphing calculator, so instead of using the GeoGebra, but this one, Desmos has good 2D, doesn't have a good 3D, and so on. So if you just plug in y equals x squared and then plug in the curvature formula, 2 over 1 plus 4x squared power of 3 over 2, you get this curve like that. It's fascinating stuff. And then we'll go to the curve, and there it is. You can play around with it, and so on. Make it bigger like that. Yeah, so you can play around with that. And I'll see the point here at 1 and 0.18. Yeah, so right there. Fascinating stuff. Yeah, so epic stuff.